So today we have Uri, who is an expert in privacy, and he'll tell us about how to compute the median.
Okay, thanks, Arnold, and thanks for inviting me. So what I'm going to tell you about is based on a sequence of works with many people, in particular with Kobbi, who is here, but also all of these other people. And what I want to tell you about is something that I feel is like one of the most basic problems in the literature of differential privacy we can think about is how do you approximate the median of the data? Like what? No, there are not too many problems which are more basic than that, I think. But like I'll show you, the answer is not that simple. So here is a statement or a vague statement of the problem that I want to solve with you today. I'll explain the problem as it's written here, and then we'll tweak it and make it forward. Okay, so the private median problem, I want to design a randomized algorithm A with the following two properties. The first property is that it solves the median problem. When you give it a data set containing points in real points, with high probability, it gives you something that approximates the median. We need to discuss what do I mean by approximating the median, but that's what I want. The second property is that I want algorithm A to be robust in the sense that if you change only one of its input points, then its outcome distribution does not change by much. So for any two input data sets that differ on one point, we call such data sets neighboring or adjacent. If you run the algorithm on the first or on the second data set, then the outcome distribution is similar. So let's start by formalizing this requirement. What do I mean by outcome distribution is similar? So what I mean is that this algorithm takes a data set containing points, real points, and it gives you an approximation for the median, which is also a real point. So for any event defined over the outcome of this algorithm, so the algorithm gives you a real number, an event is just a set of real numbers. Any event F, this event occurs with roughly the same probability between you run your algorithm on the first or on the adjacent data set. And roughly the same is usually quantified by up to a multiplicative factor of e to the epsilon and an additive factor of delta. So I don't know, probably you've all heard about it. This definition is what's called differential privacy, introduced in particular by Kobbi in 2006. And so that's the definition of differential privacy that we all know and love, at least in the literature of data privacy. So just so we're on the same page, you should think about this constant epsilon as, let's say, 1/10, and you should think about the additive factor delta as something very, very small. For today, let's just think about it as polynomially small in the size of the data set. Let's say the size of the data set to -10. Okay, so that's the definition of differential privacy. Why is that a good privacy definition? So let's think about a data set containing the information of individuals. So every individual, his information in the data set is a real number, for example, blood sugar level. And let's say that an adversary knows all of this data set except for my point. Now we take this data set, we run our algorithm on the data set, we get an outcome, and we give this outcome to the adversary. So from the adversary's point of view, he cannot learn much about my real number, about my data point, because from his point of view, no matter what was my input point, he would have seen a sample from roughly the same distribution. Make sense? So that's differential privacy. Okay, so we are done formalizing the second requirement. So I wrote it formal here. We still need to formalize the first requirement. What do I mean by an approximation of the median? But already I can say that kind of the big question, in my opinion, is what the size of the data set S should be in order for us to be able to solve this problem, achieve both goals simultaneously. I want the size of the database to be as small as possible. Then I can solve the problem privately with a small data set. And the motivation, so like I said, what could be more basic than the median? Of course, you want to understand it, And also it's used as a building block by many differentially private algorithms. Okay, so let's formalize requirement 1. And the first thing that we need to understand is that under the constraint of differential privacy, we cannot hope to get an exact algorithm for the median. That's very simple, because if that's my data set, then the exact median is exactly here. But on a neighboring data set, this point might move to the end of the world, and then the median could shift by a lot. So any case, that's a deterministic algorithm. Its distribution, its outcome is this on one data set, another on the adjacent data set, and it's not differentially private. Make sense? Okay. Okay, so we need to approximate the median. What can we hope for? So maybe the first thing you would think about, and there are a lot of works that aim to use this notion of approximation for the median, is that I want to come up with an output y that's close in distance to the actual median. Sounds good? Okay.
It's too hard. I mean, if your data set is huge, then, right? I mean, if there's big variance between the endpoints, then you cannot achieve that.
Right, I agree. That's why this option is maybe not optimal. So here is a picture that illustrates this problem. That's the exact median, and you want to be close to it. But on like the example before, on a neighboring data set without this point, or with this point moved to the end of the world, then the median shifts to here or to here, and kind of if you want to approximate it by distance, your noise is going to have to be huge in some cases. In specific cases, you might actually get a good approximation for the median in the notion of distance, in case there is kind of a concentration of points close to the median. The intuition is that if that's the case, then deleting or shifting the actual median only changes the true median by a very little distance, and a small amount of noise would hide this. So like I said, there are several papers that study this setting. It's a reasonable setting. The first paper that studied it is also by Kobbi and Sophia and Adam Smith from 2007. But maybe these two pictures say that it might not be the best way to quantify the error of the approximation, because we could only get valid answers or meaningful answers for under specific assumptions on the data or the data distribution. Okay. So another way to quantify the error is, instead of approximating by distance, we want to approximate the median by length. What do I mean? I want to find a point such that the number of input points to the left and to the right of it is roughly identical. Make sense? Okay. So first, if you can achieve that, then it actually implies approximation by distance when there is concentration around the median. So it actually gives you also the previous error measure. The other direction is not always true. And I think, at least I think that it's more, it has a better semantic than approximation by distance, because at least I understand what I'm getting. If I'm close to the median, I'm close in distance to the median, I might be like outside of the interval where all of the points lie. Okay. And okay, so just a remark, the outcome of the algorithm is not necessarily a point from the data set, it's just a point on the real line. Questions so far? Okay. So I edited this requirement 1. I'm not done tweaking the problem, but at least I have the privacy constraint written here, and roughly the utility requirement also written here. So that's the private median problem. And the first step towards solving this problem is to notice that we can actually focus on the following much simpler problem. the private median problem asks me to give an element with rank roughly half. Let's forget about this roughly half. Just give me a non-trivial median. Something with rank strictly bigger than 0 and strictly smaller than n. Just something, you know, in the convex hull of these points in one dimension. So if, let's call this the interior point problem, all I want to do is given n input points, I want to privately come up with a point between this point and that. For example, that's a perfect outcome. So it's a simpler problem because I'm only asking for a non-trivial median, and also there is no error measure. You either succeed or you fail. Okay. And the simple observation is that if you can solve the private interior point problem, then you can solve the private median problem. How? Take your input data, ignore all of your input points except for the points in the middle, the amount of points that you need in order to solve this problem, and then
you have to distinguish between points in the middle and points not in the middle.
I sort it and I just take the middle points, the n middle points.
But how can you sort privately?
So okay, that's a good question. Let's say, so all of these points are your original data points. Let's say that one of these points were to change. I claim that would change the surviving points by only 1 point. So like a neighboring data set that you begin with translates to a neighboring set that you operate on, and your solution to that problem hides this single difference. Make sense? Okay. A private algorithm for the interior point problem, its privacy constraint says that it hides an arbitrary change to a single point of its inputs. And this kind of a simple reduction has this property that if you were to change one of your original data points, it would change only one, at most one of the surviving points. And that change is masked by the private algorithm for the interior point problem. Make sense?
I didn't yet understand how you know to distinguish between the middle points and not.
I have the data. I sort it and I take the middle
Plus, you
points.
see the data.
I see that. Okay, that's
all right. Right. So you see all the data. You just don't want to give your outcome to depend on it directly.
Exactly. So the privacy requirement, we have several settings in the literature of differential privacy, but the most simple setting is where you trust the data curator with all of your data points, and you just want to make sure that the outcome distribution, okay, you protect only against an observer.
So just take the epsilon and middle ones, and then you kind of say, then your problem is enough, because this will give me.
Yeah, you just take the, let's say that you can solve the interior point problem using n points. Then you take a data set of, I don't know, 1 million endpoints, you just keep the middle endpoints and you find an interior point of them. So that would be a great, that's a valid outcome for the interior point problem. And it's going to be a great output for the median problem. Make sense?
Yeah, the only one caveat, I guess, is that this delta will depend now on smaller set. Like it will be inverse polynomial in a smaller set, so you could be.
That's right.
Distance there.
That's right. But so yeah, I agree. But in this case, I would take delta to be 1 over polynomial in 1 over the size of the entire data. I would just run this private interior point algorithm with a smaller delta. Okay. Okay. So n is the size, I didn't say it yet, but n is the size of the data that I need in order to privately solve this problem. The interior point problem.
Yes. Why is it important that it's interior point? After you do the reduction, why it will not work the same argument or just some point?
So, interior point, I mean somewhere just in the convex hull. That's what I mean.
Including the
Yeah. Okay. And so this discussion shows that the private interior point problem is equivalent to the private median problem. Of course, if you can solve the private median problem, then you can solve the private interior point problem because you get something with rank almost in the middle. And this induction shows that the other way is also true, and also the size of the data that you need in order to solve the private interior point problem, that's going to be exactly the error in rank for what you get from this reduction when you use it in order to solve the private median problem. Okay, so these two problems are equivalent, and we can forget about the private median problem and just focus on the private interior point problem. Yeah.
What about the additional error that you get from solving the private interior point problem? So you aren't getting like an actual median, you're just getting something in the inner N.
Yeah.
And the claim is a kind of N is small with respect to the entire database, so getting even within a rank N is good enough.
Yes, exactly. So the claim is that if you have an algorithm, a private algorithm that solves this problem, and it manages to solve it with a data set of size N, then you can use it in order to construct a private median algorithm with error at most N in rank. So if your data is a median N, then go ahead.
With the error half of them.
Sorry?
With the error half of them.
With error half it, yes, exactly. Okay, so that's the private interior point problem. We are almost done tweaking the problem. That's almost the final statement of the problem, just one more tweak. And again, the main question that I want to be asking today is what should N be in order for me to be able to solve the private interior point problem? That's my goal. So, two simple warm-ups. Clearly, we cannot hope to solve this problem when N equals 1 on a data set of size 1, because if that's the data set, that's the only interior point. I have to return this point with high probability, but if it shifts here, then I'm doomed. I cannot do it with N equals 2, because on the red input, I have to return something in this interval, but on a neighboring data set where this point shifts here, I suddenly have to return from this interval, and it's compilation error or something. Okay, so N equals 1 doesn't work, N equals 2 also doesn't work. And actually there is a lower bound that I plan on showing you partially today, saying that, as I stated it, this problem is unsolvable. You cannot solve this problem over the real line. You have to assume that your points come from some finite grid, and your sample complexity, your N, must grow with the size of this grid. Okay, so let's change the problem. That's the final tweak. I added a grid here. Let's call the grid X. And I replaced the real line here with the finite grid X. Okay? Makes sense? I'm done tweaking the problem, I promise.
Wait, so what is the bigger or equal in the grid?
Oh, so
Oh,
that's
you
just
mean they're just integers? You discretize the problem.
either either integers, or it's just an arbitrary subset of R finite.
Mhm.
Can you explain what the problem is in the real line?
Yeah, I'll show you the lower bound.
You can't put probably all the points in one place, another here, and then move it around.
No, because then you would just return the heavy point, right? The point that all of the points are there.
Right.
And that's actually an easy instance. That's exactly what you would do there. Okay. Okay, so we're done tweaking the problem. I copied it here to the top. And before I'll show you things about it, let's just survey what we know about it. So actually, like right from the first work that introduced differential privacy, you could use what they showed in order to get an upper bound on N, saying that N, you don't need it to be more than log the size of the grid, and it even holds when the privacy parameter delta is 0. So it's better. Okay. In 2010, again, Kobbi and two others show that if you stick with this requirement that delta is 0, then log x is the best you can do. Makes sense? So these two like early papers, they focused on the specific case when you don't have the plus delta in your privacy.
So X here is the size of the grid.
X is the size of
So
the
if the
grid.
grid is all the like integers, you cannot solve it.
No, you need infinitely many samples to solve it, and you cannot do it. Okay. Okay, so what happens when delta is not 0? Let's say polynomial is small. So in 2013, with my two PhD advisors, Amos, Beimel, and Kobbi, we gave an improved upper bound that looks like 8 to the power of log star of x. Then we improved it to 2 to the log star, and we also gave a lower bound of log star the size of the grid for solving this problem, the interior point problem. 2 or 3 years ago, we improved it furthermore, so we got it to log star x to the 1.5, so no longer exponential in log star x. And like the last piece in the puzzle is that log star, at least up to lower order terms, is the correct answer. We got it down, we shaved all of the things, and it's really log star the size of it. So to sum up what we know that log star x is like almost exactly the correct answer. What I'll show you today briefly is that it's a lower bound, and I'll give you some of the details from the 2 to the log star upper bound.
Ladder to extend to the differential or not?
So no, and it's probably not, because in the same paper we have a lower bound of 2 to the log star for the quasi-concave. Okay, but before talking about these log stars, let's see another easy warm-up. How do I get an algorithm with sample complexity logarithmic in the size of the grid? Okay, so like I said, you could get it right from the first initial work on differential privacy. What I'll show is maybe a simpler or a more clean version that follows from the work of McSherry and Talwar from a generic tool called the exponential mechanism. Okay, so here is the algorithm that gets sample complexity log the size of the grid. Your input data set is S containing n points from your grid, and you want to output a point Y from the grid that's inside the convex hull in one dimension. So what do you do? Can I write here?
Yeah.
Or here maybe is better. So you have your input points. There are points on the grid. Okay. So for any possible point on the grid, you assign a quality to it. How deep inside the convex hull is it? Okay. So the quality of this point, which is like a perfect median, it's balanced, is going to be n/2. That's the quality that's written here. The minimum between the number of points to the left of it and the number of points to the right. So the deeper you are inside the convex hull, the larger your score is. The score of like this point, so it's n/2 minus 1. And points totally outside of the convex hull, their quality is 0. And then you just output a point from your grid with probability proportional to e to the power of your privacy parameter epsilon multiplied by the score of this point Y. That's the algorithm.
But so if you have many grid points in the middle, they all have the same score.
Exactly. The
So
exact
why
same score.
this will converge?
Why would it work? You ask?
Or it's just proportional to?
Proportional. You need to normalize it. Yeah. Okay. So the privacy analysis is really simple. It's follows by observing that if you were to change one of your input points, let's say delete this point, then it affects the scores of every single point in the grid by at most one. Because if before the deletion, like the number of points to the left and to the right of me was n/2, then now it's at most n/2 minus 1. So changing one original input point changes all of these probabilities by a factor of at most e to the plus minus epsilon. And then it kind of follows that the privacy constraint holds. Okay, what about the utility analysis? So it's also very simple. We know that there is at least one possible solution with perfect quality, with quality n/2. The median has quality n/2. Okay, so what's the probability that my algorithm fails and gives me something outside of the convex hull? Outside of the convex hull is quality 0. So the probability of getting any specific bad output is at most e to the epsilon times 0. It's quality of this bad solution over the normalization factor. And the normalization factor in particular includes the perfect solution, which has quality n/2. And then there is this x for the union bound. Yes. Make sense? Like this solution, what's the probability? Let's say that it's completely outside of the convex hull. What's the probability of outputting it? It's proportional to this, which is e to the 0. What do I mean proportional? It's divided by the sum of all of these things. In particular, one of the elements in the summation is the quality e to the power of the quality of the median. Okay, so when you solve this problem, when you solve this inequality, you see that the probability of failing is small if n grows like Lorentz.
The analysis is direct or
For epsilon, for when delta is 0, yes. Okay. But it's not tight when delta is not 0. Okay. So that's a warm-up. How do we get upper bound of log x? How can we do better? Okay. So like always, my input is a dataset S containing n points from the domain X. Here is a picture, my domain X, and my input points. Okay. The first thing I do in the algorithm is I build a complete, let's say, complete binary tree over the domain X. So the leaves of my tree is exactly the elements in my grid. Okay. And I assign weights to all of the nodes in the tree. What's the weight of a node? It's just the number of input points that belong to its subtree. Okay. So the root has like full weight. Make sense? Okay. Now I have these two tables. What are these tables? The max table, I have the number of rows in the table is like the number of levels in the tree. The max table just contains, I write here, the maximal weight in this level. So the maximal weight in this level is 7. Here it's also 7. Here the maximal weight is 4. Also here, and so on. And the difference table, I just take the difference. What I write here is the difference between this and that. What I write here, the difference between this and that. Here, difference between this and that, and so on. Okay, so I have this difference table. Now I construct a data set from a much smaller domain. The size of the domain that elements in the next data set come from is logarithmic in the size of x, because the number of points in this domain correspond to the number of layers in this tree. Okay, and I just that's my input data set. Okay, so I take the first point in the new domain, I look here, 0. I don't put any input points here. The second input point, I look here, it's 3. I put 3 input points here. The next point, it's again 0, nothing here. Here, it's written 2, then 2. Okay, so I constructed a new data set from a much, much smaller domain. And then I just solve the problem recursively. And I get an interior point for the small data, the data set that it's of the same size, but its domain is small.
So now the domain is only log x size?
The domain is only log the size of x, exactly. The number of points is still n, that didn't change, but the size of the domain is smaller logarithm. So let's say that by induction,
Wait, write the number of, so the sum of all these differences should always sum up to n?
7, yeah, 12. Okay. So let's say that by induction, I solved the problem on the smaller domain and got that point here as my interior point for this data set from the smaller domain. What do? I go back to my tree. An interior point here translates to a level in this tree. And then I look at this level and I privately find a heavy node, as heavy as I can, hopefully, in this layer. So that's something that I'm skipping. You just have to trust me on it. There are easy tools in the literature of differential privacy that allows me to do this. Once I focused on a specific layer, if there is a super heavy node, I can put my finger in. It kind of is similar to the question that you asked before. What happens if you have all of your data points in this point and 1 point here? And I said, that's an easy case. I can put my finger on the super heavy point. So that's also true in other layers of the tree. If you have a heavy node in a specific layer, and you know the layer, you can put your finger on it. You won't necessarily get the heaviest node, but you will get a heavy node. So for example, here, like the heaviest node is 4, I got 3. It's also fine.
This is a private algorithm to choose like a heavy hitter in the
Yes,
set?
exactly. And it's sample, and the number of points you need to do it does not depend at all on the width of the layer. Okay, so let's say that I got this green point, this green node here. What do I do now? I just, yeah.
Do you choose it deterministically or with some random procedure? This heavy node.
It's a random procedure, as I stated it here.
It's a random procedure with some say feasible probabilities are assigned only to heavy nodes.
Yes, exactly. Okay, so once I got this green node here, I look at its two leftmost and rightmost descendants in the tree. I claim one of them is going to be a valid interior point of the original data set. Why is that? So that's an interior point of the original of the recursive data set. And let's assume for simplicity that it's like deep. It's a deep interior point. It's not like right at the edge. In the algorithm, we need to make sure that it really happens, like throwing away the endpoints from every layer, similar to the reduction between the median and the interior point problems. Anyways, for now, let's just assume that that green point is a deep interior point of this data set. Okay, so there are many input points which are bigger than L star. What does it mean? It means that here there are a lot of points. So L star in this example is here. So in this cell, in the difference table, there are a lot of numbers written here. Okay. What it means is that the number that's written here in the max table, it has to be large. Because if this number was 0, then all of the differences afterwards would also have to be 0 and nothing was written there. Make sense? if there are a lot of positive differences, starting from 0, ending up here, then what's written here has to be large. Okay, so that's also an explanation for why I know that when I run this algorithm for the heavy hitters, in this layer, I would get something. I know that there exists a node, a heavy node in this layer. Okay, just because it's an interior point of this data set, many points here, many differences here, that number has to be large. There must exist a heavy node in this layer. So let's say that I came up with this node and it's roughly heavy. If it's heavy, then there are many input points in its subtree. Right? Okay. But also, from the other side, I know that because it's deep, there are also many input points here in the recursive data set that are smaller than L star. What it means is that there are a lot of numbers written here in the differences table above the layer L star. What it means is that this cannot be n, because if that was n, all of these differences were 0. So there is a big difference between what's written here on the top, n, and the number here. So that means that there is a heavy node here. Let's say we're looking at 3. There are input points in its subtree, but it's not of full weight. So its weight is not n, and therefore there must exist input points outside of its subtree. If all of the input points were in its subtree, then its weight was n, and it's not. So there are input points in the subtree. There are input points outside of the subtree. One of the endpoints of the subtree must be a valid interior point. And now I reduce the problem from choosing one of the x input points to just choosing one of 2 possible solutions. One of them is good, and that's again something we could do easily with differential files. Just choosing between 2 possible candidates, that's an easy problem. It's not like choosing from the x potential candidates.
Wait, here you have to choose exactly one of them.
Exactly one of them, yeah.
So how does it private?
I choose them. No, I don't do it deterministically. For example, you could do it using this solution. This solution, if you only have 2 candidates, one of them is very good, your sample complexity doesn't depend on x. You got x here because of the union bound. Now you don't have a union bound.
And I mean, if you chose here in this L star to be this quick point on the left, the endpoint of your
I know. You're right. So in the actual algorithm, we need to consider one additional point. I'm cheating a little bit. You have to consider one additional point. Okay. Great. So that's the algorithm. Why does it work? Why does it give me something with sample complexity that looks like log star? Because every iteration shrinks my domain logarithmically. After log star x iterations, my domain is of size constant. I can use the previous warm-up, like this algorithm, for solving the problem once I reach the end of the recursion. Okay. What's the problem? Why does it takes me all the way to log star? Why am I stuck with 2 to the log star with this algorithm? And like the problem is that from one recursive call to the other, kind of the effect that every original input point could have on your picture here, it multiplies by 2. Why is that? Because if you think about it, let's say that that's the first iteration of the algorithm. If you change 1 point from your original data set, then the weights along the tree can change by at most plus minus 1. That's okay. But then the differences could change by 2, because you have a difference between 2 weights. If each of them changes by 1, then the difference could change by 2. That would determine the weights in the next iteration, and then again, then 1 point would affect the weights in the next iteration by 2, and then the differences table in the next iteration by 4, and so on. And that's the problem. That's why when we reach to the end of the recursion, we have a domain of constant size, but the effect of every single original input point is large, exponential in the number of recursive calls, and that's why I end up with this bound on n with this algorithm. Okay, that's what I wanted to tell you about.
Could you tell us maybe where exactly introduced the additive error? How it helped you? I mean, this is, I guess, the big difference.
Additive error of what?
The delta you have, like in the
Yes.
differential privacy.
Okay, so the points where I used it is here. When I select the heavy node from the layer. That's sorry. So that's something that I didn't explain, but I just claimed that there is some basic tool that allows you to do it without any dependency on X. That's only when you have non-zero delta.
Mhm.
Otherwise, you cannot. Okay. Okay, so that's what I wanted to tell you about the upper bound. What I kind of sketched. It's basically all of the details would get you something exponentially log star x, but like I explained, we have a better algorithm which takes you all the way down to log star x. Like the difference is that it's still kind of a recursive algorithm that embeds your input points in a smaller domain in a way that allows you to go back with an interior point, but the embedding is different. It's more complex. Okay. Questions so far about the upper bound? Okay. So I'm done with the upper bounds. Before I'll show you the log star x lower bound for when delta is not necessarily zero, here is another warm-up. Let's stick to the case where delta is zero. That's a harsher privacy constraint, easier to show lower bounds for. And it's also from a paper by Kobbi and two others. It's these kind of lower bounds for when delta is zero. In the literature of differential privacy, we at least used to call them packing arguments now, and everybody knows them already, so I'm not sure if people are still showing them. And here is the argument. That's the entire proof. So let's say that my domain is all of the integers from 1 till x. And remember, delta is 0. Okay. Now, this algorithm, I suppose that I have an algorithm that solves the interior point problem stated above. Then, in particular, if you take some number L between 1 and x, and you construct a database containing n copies of this point L, then the algorithm has no choice. The only interior point is L, and it has to output this valid solution with high probability, say with probability 0.9. Okay. But if you look at this requirement of differential privacy and forget about delta is 0, then if you change one point in your data set, the outcome distribution changes by at most a factor of e to the epsilon. Then change another point, the outcome distribution changes by at most another factor of e to the epsilon. Change another input point and so on, replace your entire database with something completely different. The outcome distribution cannot change by more than e to the epsilon n. So what I get from that is for every L, if I run my algorithm on the all one's input, the database containing only the point 1, it has to output L with non-zero probability. At least the probability that it would output it here times e to the minus e to the epsilon n. And that's for every L. So if I run my algorithm on the all ones data set, what's the probability of it failing? On the one hand, it's at most 1/10 by the utility constraint. And on the other hand, from this line, it's at least 9/10 times e to the minus epsilon n for every L. So there are x minus 1 such L's, and I get this inequality. Solve it for n, you will get that n is at least log s. Easy? But that's only for delta is 0. When delta is not 0, what breaks? I don't have this argument. Because every transition you replace one point by another, it's not only a multiplicative factor, but also another additive factor of delta. And then after roughly log 1 of over delta changes, you get nothing. Okay. So what can we say when delta is not 0? So here is the idea of the lower bound. What I'm going to show you, the theorem of this lower bound, is that there exists a distribution, let's call it dn, over databases of size log x. So it's a distribution over data sets. It's not a distribution over the domain that I sample IID elements from it. It's a distribution over data sets, over n tuples, with the property that every private algorithm fails with probability at least 1 over 4 to find an interior point of a data set sampled from this distribution. So it's a hard distribution that is hard for every private algorithm. Okay? And the idea of the proof is by induction. And the base case is trivial. The base case is n equals 1. Let's say I have a domain of size 2. Then clearly a private algorithm cannot solve the private interior point problem when the data set is of size 1. We said it already. Here it has to output 1. Here it has to output 2. Privacy says that the outcome distribution cannot change. Compilation error. Okay. So the base case is trivial. And now in the induction step, let's assume that I have a hard distribution over elements, over data sets of size n, and use it in order to construct a hard distribution over data sets of size n plus 1 over a much, much larger domain, exponential in size. Okay. Nothing happened. I just copied this statement of what I'm going to do in the induction step. Here is how I construct the next hard distribution. Okay, I already know by induction that dn is hard. I want to construct dn plus 1, which is hard. First, I just sample n elements from the hard distribution that I already have. I sample n points from dn. Here's an example. Let's say that I got these 4 blue points. Yes. Yes. Yeah, sorry.
So X is fixed here? The grid.
The grid? Yeah, so you could think about it as always the integers. The question is how many integers do you have? Okay. You could always stretch it. It doesn't, in this problem, it actually doesn't matter. What kind of a grid do you have? Okay. So I sampled the data set from the hard distribution dn, and now I sample one point uniformly from a much, much larger domain, exponential in size. So like if x, I don't know, you have numbers here between 1 and 6, here suddenly I have a huge number. Sampled uniformly from the integers between, I don't know, 1 and some cap. Okay. Now, for every I between 1 and n, I have n input points here. I construct a new point in the large data, in the large domain. How do I do it? Let's see it in the picture. I think it's easier. I look at the first input point here. It's 4. Then I construct y1, which has the first 4 digits identical to y0. I copy them from here. And the rest of the digits I just sampled uniformly. Okay. Now, the second point, x2 is 5. I construct or I sample an element y2, where the first 5 digits, I copy them from here. And the rest of the digits I just sample uniformly. Same from y3, I look at x3, it's 2. I copy the first 2 digits from y0. sample, and so on. Make sense? That gives me, or that defines a distribution over data sets of size n+1 over a domain which is exponentially larger. Because the domain has to be exponentially larger because I look at the value of points here, and that's the number of digits in my new domain. Okay. Okay, so like we said, we started from a hard distribution dn. We constructed a hopefully hard distribution over n+1 elements from a much larger domain. And my Cohen goal is to show that if dn is indeed hard, then the distribution I constructed here, dn+1, is also hard. If you could do that, then because n grows by 1 in every iteration and the domain explodes exponentially in every iteration, then that gives you a lower bound of log star. Okay. So again, what I want to do now is prove that dn+1 is hard. I don't have a lot more slides, but if it's like a strict deadline,
very strict.
okay. Okay. So let's assume that I have a differentially private algorithm that solves dn+1. I want to show you that if that's the case, then I can construct a differentially private algorithm that solves dn, and that's impossible by the inductive assumption. Okay, so let's assume that I can privately solve dn+1, and let's say in the example that I ran this algorithm and got this point as my outcome. I want to translate this outcome to an interior point of the original axis. How do I do that? I just look at the length of the longest common prefix between the purple outcome that I got here and the y0 that I started with. In this example, it's 3. These two numbers agree on the first 3 digits. That's my outcome. I output 3. And I claim that that's going to be an interior point of the original input elements. It's public in the reduction for me. I designed the algorithm for dn. I invented y0 myself. And now when I run the supposed algorithm for dn+1, in his point of view, it's not public. That's one of its input points. Okay, but I can use it y0. I invented it. Okay. So why is let's call it this x star, the length of the longest common prefix, that's x star. I claim that it's an interior point of the original axis. Why is that? So first, it's easy to see that the length of the longest common prefix cannot be smaller than the smaller xi here. Because if it's smaller than the smallest xi, then that point is outside of the convex hull. Like all of the numbers here, if the smallest number here is 2, then all of the numbers here starts with 5, 4. If you give me if the length of the longest common prefix is 1, then it starts with, for example, with 5, 8, then it's out of the convex hull. Okay, so x star cannot be too small. Why can't it be too big? And that's because what you were trying to put your finger on, or because the algorithm that solves dn+1 supposedly, he is private. And he is private also with respect to y0. So whatever it gives me, it should also give me roughly the same answer, even if I didn't give him y0. So let's suppose that I ran my algorithm and got the same answer without y0. Then look at all of the other points here. None of them knows the next digit of y0. Like even conditioned on all of these numbers, the next, if I don't give you y0, the next digit of y0 is still completely uniform. And the probability of this algorithm guessing it is at most 1/10 without giving it y0. because it's private, even when I do give him y0, the probability of him guessing it stays roughly 1/10, which is small. So a private algorithm cannot guess the next digit of y0, even when I give it y0, and therefore the length of the longest common prefix between the outcome and y0 cannot be too large. Okay, so the length of the longest common prefix is not too small, not too large. It's an interior point of the original axis, and we solve the problem. Great. So privately solving dn plus 1 implies privately solving dn, which is impossible, and therefore dn plus 1 is hard. Okay. So that's what I wanted to tell you about today. I guess like the main thing I showed you is I think that we finally almost exactly understand this problem of privately approximating the median of the data. The answer is log star the size of your grid. The way we do it is by analyzing this simpler interior point problem. And like the interior point problem or the median, it has many applications for many differentially private algorithms and tools, and that's it, I guess.
Questions?
Is there a gap there now between 2 to the log star and 8 to the log star?
No, we also have an improved algorithm with 2 to the log star. So, but in all of the places we used quasi-concave, it's still possible that you could somehow do it another way. Like that's currently the main workhorse for discrete half spaces. And it's still possible that the discrete half spaces you could solve via some other tool and get it to log star or polynomial in log star.
And is it still working in classical algorithms or does this work? We leave it on the exponential.
No, I don't think that it translates to a lower bound of 2 to the log star in that application. Yeah. In the paper we used it for, I don't think that the lower bound translates to lower bound there.
What related problems like average or norm estimation, stuff like this?
So at least historically, the most related problem was in the context of private pack learning. So your input points, and when you see it, you'll see that it's almost exactly the same. Your input points on the line are labeled by either 1 or 0. So you have these points sampled from some distribution, and you want to come up with a classifier that when I give you a new sample, allows you to predict its color. So in this context, it's roughly the same. You want to find kind of throw away additional points that you have, such that the number of points of red and black points you have is each of them is of size n/2. Come up with an interior point of them that gives you a classifier with small error. So that's at least historically, I think, one of the most related problems. And this upper and lower bounds say that they translate exactly to upper and lower bounds for this problem, because it's basically the same problem. But there has also been other follow-up works, not by me, that ask, okay, what if your classifier for threshold functions, for this one-dimensional threshold functions, itself doesn't have to be a threshold function. Like what if you could give me a function that looks like this, which is kind of crazy looking function, but somehow still provides you good accuracy. The follow-up works, not by me, show that or extended or show the different lower bound of log star x that holds even here.
Also robust statistics. You have multiple experiments and you take the median of them as the most common statistic, the most unbiased number, it's most rare.
Other questions? So let's tell Corey again.